Now that we've looked at the variances, let's go ahead and continue on and look at the means. Okay, the data types applicable, once again, are both interval and ratio. Whenever we talk about a mean, you know we're talking interval or ratio. It just does not make any sense to calculate a mean for nominal or ordinal data. Now, there's two main scenarios that we'll be concerned with when we start talking about the difference between two independent means. We say the difference because the way the hypothesis test is typically written, we subtract one mean from the other. But really, what we're doing is we're comparing two independent means. We don't have to necessarily think in terms of the differences. Now, first of all, the very first scenario is a situation when we actually know sigma. Sigma is known. If sigma is known, just like earlier on the one sample t-test, we'd use a z-test. Remember earlier we'd use a one sample t-test because we didn't know sigma. If we did know sigma, we use a one sample z. The second is when sigma is actually unknown, which is more realistic, and then we'd use a t-test. In this case, both of these would be a two-sample z-test and a two-sample t-test. Now, because a scenario where you would actually know sigma is a little bit difficult to imagine, I'm not even going to go into the two-sample z-test in the videos. I'm going to concentrate on the two-sample t-test. Well, if you can do two-sample t-tests, you can certainly do two-sample z-tests. It's not that big of a deal. But realistically, in the real world, it's very rare you'd end up doing a two-sample z-test when we're talking about comparing means from two independent samples. Okay, let's take a look one more time at this data. This is the same data we just used a moment ago for the variances. If this video is new to you and you haven't looked at the other one yet, then you probably want to pause the video, enter the data, the current technique, put it in L1, the new technique in L2, in case you want to follow keystroke by keystroke with me. Go ahead and enter that data and then continue the video in a few moments. Okay, the assumptions. The assumptions that we're going to look at here in order to use a two-sample t-test are identical to what we did for the variance, the f-test. The data came or was obtained from two independent populations. Well, we have the current technique or the old technique, however you want to phrase it, and this new technique. They're assembly processes. There are no connection between them. They're independent processes. The distributions of both populations are normal. Well, we already addressed that. We did normal plots, and I'm not going to do them again. I'm just going to draw what we'd start off with, and we said they're okay. I'm going to put down here from the previous example. If you haven't looked at the previous video yet when we did the f-test, run the normal plots and you'll see they're fine. Now, are these two data sets independent of each other? Yeah, I just justified that. They actually come from two different processes, so that's not a problem. So, yes, they are. Of course, you could never, in my class, say yes. You'd have to explain why. Like I just said, two separate processes. There's no connection. That's sufficient. We don't need to go too terribly deep on that. Okay, the normality assumption. The CLT does not apply, and like I just said, we already did normal plots. I'm going to say okay here. If you did an f-test first, you already had the normal plots. If you're going to do a t-test with the same data, you don't have to do normal plots again. You already did it once. You know what they look like. Now, the two-sample t-test actually has two different forms. So in order to determine which form we're going to need to use, we need to determine whether the variances are actually similar or not. If the variances are similar, then we're going to do what's known as pooling. We'll pool the variance. To pool the variances simply says, well, if you pool your efforts, you're taking efforts of more than one person and putting them together, right? Well, if I pool the variances, I'm going to take the variances, the sample variances, and put them together. That's all it really means. It's a type of weighted average. Now, we need to make that determination whether we should pool these variances or not. And to make that determination, we will actually use an f-test. Okay, to give you a better idea here what's going on mathematically, I want to show you the test statistic. So T actually equals, I'm going to say the mean of the first group minus the mean of the second group. Those are the differences I was talking about earlier. If the means are the same and I subtract them, I'll get 0. So 0 would mean that there's no difference between them. If I subtract and get a positive number, that would suggest the first mean is bigger than the second. If I subtract and get a negative number, that would suggest the second number is bigger than the first. And then we divide by the standard deviation. But the standard deviation will look like the variance of the first one divided by the sample size of the first plus the variance of the second divided by the sample size of the second. And I need the square root of all of these. Now this is if we do not pool. That's what the test statistic will look like if we do not pool. Now if we do pool, the test statistic will look like the difference of the means divided by the pooled variance times 1 over n1 plus 1 over n2. And of course I want the square root of all of that. Now this is if we do pool. So you see, these two test statistics will have different values. Well, if you recall, the t distribution is centered at 0, just like the z is. And if I use, I'm going to call this T1 and T2, just so we can separate them. If I don't pool, perhaps T1 will end up here. And I'm assuming, for just sake of discussion right now, I'm doing a right-tailed test. That means that this area here is my p-value. Now, if I do pool, T2 may end up, say, here. And this is my p-value. Now, if these p-values are anywhere near what you set for alpha, one could result in rejecting, and the other could result in failing to reject. If the p-values are very incredibly small, that's not going to matter. Yeah, you're going to get different p-values, but in terms of decision, you're still going to end up in the same place. You're still going to reject if the p-values are very small. But we need to be careful of this because you could actually come up with a different, or come to a different conclusion because you failed to pool when you should have, or you pooled when you shouldn't have. Now, the actual pooling, and you don't have to do this by hand because your calculator will handle it, but this pooled variance here is actually a weighted mean. It's n1 minus 1 times the first sample variance plus n2 minus 1 times the second sample variance. And this whole thing is divided by n1 plus n2 minus 2. This is actually just a weighted average where all I'm really doing is I'm taking the first variance, I'm going to weight it by the degrees of freedom, which is an indirect way of weighting it by the sample size. Then I'll take the second variance, sample variance, and weight it by its degrees of freedom. So in other words, if one had a higher sample size, higher degrees of freedom, it should have more of an impact when I combine them. So this is a way of weighting it based on the sample size, degrees of freedom. And then the combined degrees of freedom, is one way to look at this, is this n1 plus n2 minus 2. That's not exactly true, but well, yeah, actually it is. That's fine. So anyway, that's the process there. Now, what have we done so far? Well, I want to think about this step by step. We start off by saying, you know, I want to compare two independent means. And then I looked at the assumptions, and I'm just going to say here that the assumptions were okay. And now I need to decide for my actual two-sample t-test whether I'm going to pool or not. So I need to decide pool equals yes or pool equals no. I need to make that decision. And how will I do it? Use an f-test. So here I am working on a hypothesis test for the difference of means, or comparing two means. And inside that hypothesis test, I'm going to have another hypothesis test based on the F distribution. So I'm going to say H naught, my null hypothesis, is the sigma squared old divided by sigma squared new equals 1, suggesting the variances are similar, they're the same thing, versus HA, sigma squared old over sigma squared new is not equal to 1, suggesting they're different. Now, if I reject H naught, rejecting it says that they're different, that implies, well, if they're different, we will not pool. That would imply that pool equals no. And the only reason we're doing an F test here is to make this decision, to pool or not. Now, if I fail to reject the null hypothesis, that would then suggest that the variances may in fact be similar. And if they are similar, that's when I want to pool them to get a better estimate. That suggests pool equals yes. Again, the only reason I'm actually doing this null and alternative hypothesis, getting the p-value and making a decision is so that when I do my other hypothesis test about the means, I will know whether I should or should not pool. So now that I have this information, I will then come back and continue with the hypothesis test. Oops. For the means. So I start off thinking about wanting to talk about the means. Well, before I can actually talk about the means and actually complete it, I need to decide whether I'm going to pool or not. So I'm going to do an F test. Based on the F test, it will tell me pool, yes or no. Now that I've done the F test, and now I come back and actually do the hypothesis test for the means. So I'm going to actually be dealing with two different p-values just to get at the answer about my means. The first p-value is nothing more than should I pool or not. The second p-value actually tells me whether my means are different or one's greater than the other or whatever the question actually was. Okay, so that's the thought process. So let's go ahead and complete that now with our data. So here I go. I need to decide whether or not I'm going to pool. Well, remember, I'm still comparing two independent means. That's the question. That's what I'm trying to get at. Along the way, I need to decide whether I'm going to pool or not. So my null hypothesis could be a sigma squared old technique over the new techniques 1. And here, if you notice, when I did the F test for the variances in the previous example, here I had greater than, because I was looking at did the new process reduce variability. Now, I don't really care if it reduced variability or not. All I'm interested in is, are they similar? If they're similar, great. If they're dissimilar, I need to know that. Dissimilar does not suggest one direction or the other. It does not suggest specifically new is bigger or specifically new is smaller than the old. Just simply, are they different? So this is going to be not equals. Alpha, I'll stay with an 0.5. Now let's switch to the calculator. I'll go to stat, test, to sample F test. It's the same as I did before, only this time I am not interested specifically in the new having smaller variability. I'm interested in not equal. So I'm going to make that adjustment, hit calculate. There's my new p-value. So I'll come back to my computer. I'm going to say my p-value is 0.01592. Clearly, this p-value is substantially bigger than my 0.5. So my decision will be to fail to reject. If I fail to reject, I'm saying, you know, this may be true. I don't know if it's true or not, but the evidence suggests that, you know, I can't prove they're dissimilar, so they may be similar. This suggests my conclusion here is simply going to be, because they may be similar, pool equals yes. That's it. So there's no conclusion whether one variance is bigger than the other and all that. The conclusion here is simply pool equals yes. If I rejected, I would say pool equals no. I need the answer to this question to complete my next hypothesis test, which is the whole goal of this whole analysis right here. So now, once that's been decided, I'm going to continue with the two-sample t-test. Now, the whole idea here is, does this new process reduce the number of, on average, the number of blemishes? So I'm going to work this as the mean of the old. And you can write this a couple different ways. I'm going to write it like this, is equal to the mean of the new. You could write it as a difference. Minus the mean of the new equals 0, which is saying the exact same thing. Then the alternative hypothesis, the mean of the old is greater than the mean of the new, which means if I wrote it in terms of differences, the mean of the old minus the mean of the new is greater than 0. These say the same thing. Depends on how you want to look at it. Alpha, I'll stay with 0.5. There's no reason to change it. There's nothing in the problem that said at a different significance level. And I'm talking about blemishes, so to me, 0.5 is fine. I don't really need to worry about at the 0.1 level or something like that. It's not that hugely important. I mean, it's an important process, but I'm not going to dwell on that too much. Okay, so now I'm going to switch to my calculator. And when I do, I'll go to Stat, Test, and I'm going to go right here to option 4, which is my two-sample t-test. I will select it. I'm working with data. Now, with these two samples, the mean of the old equals the mean of the new is the way I wrote my null hypothesis. Left to right, old, then new. Well, on the calculator, left to right on paper corresponds to top to bottom. So old was my first data set going left to right. So here, list 1, list 2. List 1 needs to be my first data set. These have to agree with the way you wrote your null alternative hypothesis. So L1 refers to the old data, the current process. And L2 refers to the new process. And my alternative hypothesis is going to be greater than. And then the next question here is whether I should pool or not. Well, we failed to reject when we did the F test, so the answer to that question was pool equals yes. So now I can come down and calculate, or if you want to draw it, I think I will calculate. I have a p-value of 0.0697. So we'll switch back to my computer, and I'll write that down. P-value is 0.0697. Now, if I have an alpha of 0.5, whoops, that's not what I wanted. Oh, hang on. I just made a mess of that, but with the wonders of technology, it's very easy to fix. That's what I wanted. Now, I have an alpha of 0.5. This p-value is bigger. So my decision here would be to fail to reject. The conclusion, there is not enough evidence to suggest the new technique or the new process, however you want to word it, reduces the number of blemishes. Not enough evidence. At least not with a significance level of 0.5. The p-value is 0.0697, basically 0.7. If you had a higher significance level that you're comparing it to, then you may come to that conclusion. So, based on the analysis we've done, we've looked at this new technique and we said, all right, will it reduce variability? Answer, no. That means there's no statistical evidence to suggest that it will. Not at the significance levels we were working with. Okay, well, if it doesn't reduce it, I mean, it's not making variability any bigger, so there's no harm done there. Will it at least reduce the number of blemishes? No, not at this p-value, not at this significance level. So what this is saying is this new process, statistically speaking, from the data that we gathered, that's important, from the data that we gathered, there's no reason to switch to it. It's not going to reduce my variability. It's not going to reduce the average number of blemishes. Hey, if it did one or the other, there may be a reason to switch to it. But based on this, no reason to do it. Okay, so that's going to wrap up for this piece. In the next section, let's take a look at what happens if we have a violation of our assumptions. Oops, don't want to do that yet.